geometric sequence, whereas our arithmetic, we added something each time. This time we're going to multiply by something each time. So it would be a sequence. Where the quotient, or we can also call it the ratio, between two consecutive terms is constant. So this time, instead of like subtracting two numbers to figure out what we're adding each time, we're going to divide by two numbers to figure out what we're multiplying by each time. So because this is a new type, it does have a new general equation. So here is our equation. It is a sub n equals a sub 1 times r to the n minus 1. Again, a sub 1 is our first term. R is that ratio, or whatever we're multiplying by each time. And then n is whatever term it is that you're looking for. Also remember that you will have a note card on this quiz. However, we still probably want to write that down so that we have it. Alright, so this says write an equation for the nth term for each geometric sequence. So, on this first one, what are we doing? What are we multiplying by?
4.
How would I figure it out if it wasn't like super obvious? What?
Divide like the second number by the first number.
Yeah, you just have to divide two consecutive ones. So like 8 divided by 2 gives us 4, or 32 divided by 8 also gives us 4, right? So our r is 4. So then we're just using that a sub n equals a sub 1 times r to the n minus 1. Can I multiply my 4 and my 0.5 and get 2?
No.
Why not? Because what? Yeah, so remember that our order of operations says that we have to do exponents first, right? Well, we have a variable in our exponent, so we can't get rid of our exponent, which means that we can't continue on in our like simplification. So we just have to stop there. That's our formula. Yes? So then if I asked you to find the third term, what would we do? Plug in 3 for n. So you'd have 4 to the second power, which is 16 times 0.5, so you would get 8, or so forth. Does that make sense? We all okay with that? Yes? Questions? Alright, what's different about our next one? So they give us an R, which means it's still geometric. But what's different? It gives us the fourth term this time instead of the first term. Yes? Okay. Do we need the first term? Yeah, for our formula. So what could we do instead? What does that mean? Do what with it?
Make it negative. Something like that, maybe.
Not quite.
Divided by 6.
Well, we could divide what by 6? How many times? That's right. Opposite direction. 3 times, right? Because I'm already at 4, so I just have to go backwards 3 times to get to 1. Yes? Yes. So that would be 6 to the 3rd. Well, or in other words, notice that if I put a 5 in here, and I know that that is the 4th term, right? I end up with 5 equals a sub 1 times 6 to the 3rd. What is 6 to the 3rd? Like
190.
So 6 times 6 gives us
36.
36. 36 times 6 is 196.
What'd you say? 92.
So that's our a sub 1. So now, do we have all of our pieces to plug it in? So we have 1 divided by 196 times 6 to the n minus 1. And that would be our answer. What questions do we have there? Yes. So what are our different types that we've talked about so far?
Geometric.
Geometric,
Algorithmic.
arithmetic. We talked about one more yesterday. Not quite.
Where's my notes?
Recursive, right? Remember, recursive was the one where we had to use the previous term to find the next one. Okay? The reason I asked that is because we need to be able to. Too fast. Alright, identify what type of sequence or series we have here. So on this first one, I have 1, -3, -7, -11, -15. What are we doing? Subtracting 4. So what type of sequence is that? Arithmetic. What are we doing on the second one?
Multiplying with 3.
Okay, which means that it is.
Geometric.
Okay, what are we doing on the next one?
Oh,
Neither.
neither.
Neither. So, like, notice that on this first one we added 9, but then on the second one we added 2, so it can't be arithmetic. On the first one we multiplied by 4, but then on the second one we multiplied by 7 halves. Yes, no, sorry, 7 thirds, 7 sixths, whatever. So it's not geometric, so it's neither. And what about our last one? What is that? It's not geometric.
Oh, arithmetic.
It's not arithmetic.
Oh, probably neither.
It's recursive, right? Because notice that my a sub n plus 1 is based upon my a sub n, which means the next term is based upon the last term, which means it's recursive, which is not either one of those. Yes? Are we all okay with that? Yes, no, maybe? Alright, we ready to look at some application problems?
Yes. What's that corn?
No way.
That was neither. I don't say right.
Okay. Alright, so it says Jose averaged 123 total pins per game in his bowling league this season. He hopes to bring his average up by 8 pins each new season. Write an equation to represent the nth term of the sequence. During what season will Jose average 107 per game? Or 187 per game. So what do we need to do first? Write an equation, alright? But it's helpful for us to pick which equation we're writing, yeah?
Yes.
So remember, we have 3 types. We have arithmetic, geometric, and recursive. Yes?
Yes.
So what does it tell us is happening each time?
Is adding 8.
He's adding 8. So if I'm adding 8, which one of my 3 is that going to be?
Arithmetic.
Yeah. So what's our general formula for that?
A1
Not times.
plus A1
Plus
N minus 1.
N minus 1 times D. Okay, so what is A sub 1? Or the first term, or the first number.
123.
Okay, and then what is he hoping to increase it by?
8.
8. Okay, so that's my D value. And then we just want to simplify a bit. So we would distribute, that should be 8, and then subtract. So 123 minus 8 gives us 115. Yes? So that would be our general equation. And then what do we want to do with it? That is our interim equation, because the n represents whatever term we're trying to find. So we want to plug 187 in for n?
No. Wait.
Oh, I want to plug it in for a n? Why?
Because that's the number in the term.
Yeah, because that is the total, or that's the amount that we're trying to get to, yes? And so we're trying to figure out what term, or what number, or what, I think, season, do we have to plug into n to get that number? Yes? So we would subtract 150, divide by 8. What do we get?
9.
So it would be the 9th season. Are we all okay with that? Okay, let's look at another one. We still have 4 more slides left. So it says a small business sells $10,000 worth of skincare products during its first year. The owner of the business has set a goal of increasing annual sales by $7,500 each year for 9 years. Assuming that this goal is met, find the total sales during the first 10 years this business is in operation. So again, what are we doing this time? Adding. How much?
7,500.
Okay, which tells us we have what type of sequence? Okay, now this time, what are we looking for?
How much it'll be after 9 years.
After 10 years.
Yeah.
So am I wanting to know how much she makes in the 10th year?
No.
No. Oh, okay, it says total, so what does that tell us?
You want to find all of it added together.
All of it added together, so we're looking for a
Sum.
sum.
Yeah.
Yeah, so this time we're using our sum formula. Alright, so how many numbers are we adding together? 10. How much did she make the first year?
10,000.
But then now we also need to know how much she made the 10th year, yes? Right? Because that would be a sub 10. So how would we find a sub 10?
You just add 7,500 9 times.
Yeah, or we take our formula, which is a sub 1 plus 9, because it's n minus 1. Sorry, that should be 10,000. That's what it should be. Because 7,500 is our D, because that's what we're multiplying by each time. So 10,000 plus that. There we go. Yes? So what do we get there? Someone plug and chug that into our calculator. It's gonna be a big number. Oh, okay, go for it.
Not like this though.
What is it?
77,500.
Alright. So now that's what goes in here. And what do we get? So notice that I can also do 10,000 instead. So what do we get?
460,000.
What do we get?
I don't know.
He said something. 43,750.
43.
Oh wait, times 10. Wait. Oh
Yeah.
shoot.
So 430,000?
Yes. 437,000.
37.
Yes.
That? Or just thousand?
This thousand.
Some of y'all aren't great at reading the numbers there.
That owner was about to be really happy.
They would have been, yeah. Just like, oh yeah, just change that. Okay. Alright, questions on this. So again, the biggest things with our sequences and series are going to be one, okay, knowing which formula to use, okay. So like for our word problem, choosing, am I using a geometric or am I using an arithmetic? And then two, making sure that we are plugging the correct things into each of those places. Yes? You with me? Alright. We're going to look at one last one. And this is a fun one. Okay? This is called our Fibonacci sequence. It was an Italian guy, so that's why it's a fun name. Yeah, it is. So, Fibonacci, okay, came up with a specific sequence. Alright? So the way he kind of came about it was he came up with this like thought experiment. Alright, so he was saying, let's pretend we have an island. Alright, and on that island we have a pair of rabbits. One pair. Are you with me? I know it's weird, but it's okay. They're my rabbits. Alright? And the rabbits will reproduce after they have been there longer than 1 month. Yes?
Yes.
And each pair of rabbits reproduces one more pair of rabbits. Are y'all with me? Kind of? Okay. So then that means on our second month, okay, they have not been there over a month, so they haven't been there long enough to reproduce. So we still only have one pair of rabbits. Are you with me? Okay. Now, on our third month, though, they have been there long enough to reproduce. So now, how many pairs of rabbits do we have? 2. Okay. Now, on our fourth month, okay, our original pair of rabbits has been there long enough to have reproduced again. Yes? But our second pair of rabbits has not been there long enough to reproduce yet. So we have 3 pairs of rabbits. Yes? Well done. So, then on this month, now, both of these pairs of rabbits have been there long enough to reproduce. Yes?
Yes.
But this last one has not. So how many do we have now?
5.
Okay? Each pair of rabbit reproduces a pair of rabbits. So, yes, they're having 2 rabbits when they reproduce. Okay, any guesses as to what a sub 6 is going to be?
8.
It is.
Oh my goodness.
And a sub 7 would be?
13.
Yeah.
Oh
So,
my goodness.
in general, what are we doing to find the next term?
Adding the last one with the other one. Wait, okay, so like 5 and 6 to get 7.
Yes, so we're adding the 2 previous terms to get the next term. Yes? So, the way that we would write that out as like a general formula would be a sub n plus 2 equals a sub n plus 1 plus a sub n. Basically, we're going backwards 2 times to get the next one. Okay? So, this is a recursive sequence, just like in the other ones we looked at. The only difference here is that we're using 2 previous terms instead of just 1 previous term. Now, by looking at those numbers, it might not be super interesting just to like see those numbers, all right? But what we can get if we look at those, so let's see if I can draw this correctly. All right, so each of these drawing, roughly. Okay, this is not super accurate. You can't do it very accurate. Pretty cool. But each of these areas is equivalent to these numbers, right? So my first one has an area of 1. The second one also has an area of 1. The third, an area of 2. 3, 5, and 7. Okay, I could keep going, but we're not going to. You with me so far?
Yes.
Yes, that basically I'm starting here and I'm just kind of working my way out using the length and widths with those, the numbers from that, okay? So basically we're just creating a visual representation of the sequence that we just created. So, starting here in the center, if we then connect those corners from each of those, okay, it creates a spiral, which is also called Fibonacci's spiral. Okay? And the reason why Fibonacci's spiral, okay, so again, this guy just came up with this thought experiment of like, hey, what happens if I basically end up adding the two previous numbers that I got together? Here's a visual representation, but hey, guess what? That spiral occurs naturally, okay, in the known universe a lot. So this one on the upper left-hand corner is a nautilus shell, all right? You also see it in the bottoms of pine cones and in sunflowers, all right? So notice that they all start with a center, all right? And then they spiral out and get larger and larger and larger and larger. And what's interesting is that they aren't just any spirals. Not any spiral is a Fibonacci spiral, okay? The ratio between each of those numbers, all right, is this 1 to 1.618. And this is called our golden ratio. And it specifically shows up in all of these things. It also shows up in the ratio as a hurricane expands, right? As well as the way that the Milky Way galaxy expands from its center. So they all use that golden ratio that this guy created by making a sequence. Now, the other interesting side of that is that the golden ratio is not only occurring in the natural world, but it also is very stable. So if you create buildings using that golden ratio as your dimensions, they're very, very stable, which means that in a lot of your Greek and Roman architecture, which is why some of them we still have ruins from them, you will find the golden ratio in the spacing of those columns. And that's why they have stood so long. Okay? As well as in general, people find that specific ratio very appeasing to the eye. Okay, just looks nice for us to look at, which is why you will also see it a lot of times in artwork, like in Mona Lisa. And so it's like taking this small piece and expanding on it in that spiral motion. But again, specifically at this special ratio. There you go. So mathematics can explain the universe. That's your lesson for today.
Oh, that's pretty neat.
Yeah, I think so too.